So dear students, I welcome you for the today's lecture related to the designing of the skirt support and its numericals. The designing of vessel supports, the different types of the vessel supports you should know. That is the skirt support, bracket or lug support, the saddle support and the leg support. The skirt support that is used generally for tall vertical vessels, bracket or lug support that is used for vessels with diameter L by D ratio 2:3, and diameter up to the 3 to 5, 2 to 5 meters. Then saddle support they are used in case of your horizontal vessels and leg supports which are used for your small vessels. Then coming to the designing process, this of skirt support, as it is used for tall vertical vessels, so its height that is one of the major distinguishing factor for the calculation purpose of the stresses. In which we are going to discuss the dead weight of the vessel, the operating weight of the vessel. So total weight of the vessel that is to be counted, which is the summation of dead weight plus the weight of the contents. The next is related to the lateral load by the interconnecting pipes. The next is wind load and the seismic load. These are the different loads which are acting. Now out of this, the dead weight that is acting in a vertical direction, longitudinal direction, and which is trying to raise the vessel in a stable condition. However, the wind load which is acting, that is going to force it to overturn the vessel. So vertical vessel जो है वो tilt हो जाएगा या गिर जाएगा. That is what the wind load will do or the seismic load will do. Seismic load that is nothing but your earth load because of the earthquake. So the stresses because of the dead weight plus the total weight of the contents, which is the summation of W upon the pi dsk upon tsk. Pi dsk upon tsk is nothing but the area on which the total weight that is going to be exerted. So the stresses because of the dead weight. Then the stresses because of the wind load. For that purpose, we are going to first calculate the wind forces acting over the vessel. Now vessel that is divided into the two sections, that is up to the height of 20 meters and above 20 meters. So up to the height of 20 meters, the formula for wind force acting on this lower region, that is K1 K2 P1 H1 into the DO, and while the wind force that is acting above 20 meters, that is K1 K2 P2 H2 and DO, where P1 is nothing but the wind pressure acting over the lower region, and that is its value is taken as 100 kgs per meter square in general case, and for the value of this P2 that is taken as the 200 kgs per meter square, which is the wind pressure. You can do the averages also in some numericals, that is you can take the 135 kgs per meter square, that can be the average of your P1 and P2, that is depending on the height, or the data which can be obtained from the meteorological department. So this is the wind force which will be acting on the vessel, while K1 and K2 they are the constants depending on the shape factor, and the period of vibration. The K1 is the shape factor depending on is the shape factor and zero point 0.7 value for the cylindrical surface and 1.4 value for the flat plate. Well, the K2 that is the period that depends on the period of first cycle of the vibrations. That is because of the wind, your vessel may get the vibrations and its period of oscillations that depends. In the period of oscillation, period of vibration is less than 0.5 seconds, then this K1 value which is equal to the 1 and K2 which is equal to the 2 if the period of vibration is more than 0.5 seconds. Once the wind forces they have been calculated, then the bending moment that is to be calculated. So Mw which is equal to PLW into h by 2 and this is up to the height of 20 meters, and if the height is more than 20 meters then the bending moment that is calculated by using the formula PLW into h1 by 2, the same formula, this is the same formula because the resultant force that is acting on the half of the distance, that is why we are multiplying it by h by 2, that is nothing but the h1 by 2. And then PUW which will be active plus PUW into bracket h1 plus h2 by 2 where h1 is height up to the 20 meters and h2 is total height minus h1. Once the bending moment that is calculated, then one has to calculate the stresses which is acting on the bottom section. So Mw upon Z, Z is nothing but the section modulus and which is Mw upon pi by 4 dO square upon TSK. Similarly, the stresses due to the wind load that is also to be calculated. The wind load that is acting because of the stresses, if we will be looking at this, they are gradually increasing because at the bottommost section the stresses, the load that is the minimum and at the top the load that is maximum, and in such cases this wind load is acting 2/3 of the height from the bottom section. However, where is the uniform load is there, then it is acting only half the height. So if that is what we have taken Mw into h by 2. Now in this case it is the uniform wind load which is acting on this vessel. The same magnitude of this all is to be considered, even though some may look at a different length, different magnitude, but the resultant one has to take it on the half the distance. Half the distance that is to be taken, and when it is the gradually increasing, then it is 2/3 of the height from the bottom, or you can say 1/3 height from the top. And CSF, that is the load, which is nothing but CS into W. The CS is the seismic coefficient and having the value of maximum value of 0.08. So bending moment that is to be calculated for seismic load MS at a distance x, which is equal to CS into Wx square upon 3 into bracket 3h minus x upon h square. Similarly, the bending moment at the base of the column, that is of concern, MSD, which is equal to 2/3 CW into H. So the stresses that will be is equal to MSD upon Z. Similarly, we have taken or calculated for MW upon Z, bending moment upon the sectional modulus. Sectional modulus is nothing but pi by 4 dO square into the TSK, the same formula as applicable for given wind load. Now out of this, the stresses, maximum tensile stresses in this curve, that will be the minimum tensile stresses in this curve, that is because of the on this side it is the compressive stresses and on this side it is the tensile stresses that will be active. So when you take the compressive stresses which is on this side, it is the summation of dead weight plus the wind forces. Both are acting in the same direction. However, on the another direction, it is minus, dead weight minus the stresses because of the wind. Then the calculation of the skirt bearing plate, that is the FC, which is equal to summation of WA plus MW or MS, out of which is at a higher value upon the Z. Then the stresses on the bearing plate, that is calculated as the F, which is equal to 6 M maximum upon B into TB square, where TB is the thickness of the bearing plate that is to be calculated. Then the designing related to the anchor bolts, that can also be done. How many number of anchor bolts and of what dimensions of the anchor bolt has to be selected. So for that purpose, why you require the anchor bolt? Because the vessel, if it is going to overturn, so it should not overturn. To prevent this, we are putting the anchor bolts on this side or in either of the sides, so that it will not get tilted or overturned. And that is the basic purpose, to provide the anchor bolts to hold it in a vertical position. So the minimum stresses between the bearing plate and the concrete foundation, which is the FC minimum, which is nothing but W minimum upon A, that is the weight per unit area minus the bending moment upon the Z, sectional modulus. So there is a stability coefficient which is also to be calculated. FC minimum is positive or 0. Then estimate the stability coefficient for the column, or else the vessel itself is stable. If the weight of the vessel is sufficient so that it will be able to resist all the forces because of the wind or because of the seismic load. इतना हेवी वेसल है, कोई धक्का देगा तो कुछ फर्क पड़ने वाला है नहीं इसमें. So in that cases there is no necessity for providing the anchor bolts. Just for simplicity you can provide, but it is not necessary to provide the anchor bolts if the stability factor it is greater than 1.5. So if Y is greater than 1.5, it means the vertical column is sufficiently stable and there is no need to provide the anchor bolts. If the FC minimum is negative, the column has to be anchored to the concrete foundation to resist the overturning capability. That means overturning, it should not tilt and should not get collapsed. So load on the bolt that is to be calculated. So FC minimum into A, that is the surface area of the anchor plate upon the number of bolts. So stresses on the bolt, which is equal to load on the bolt upon the area that is to be calculated, and the area for the anchor bolt that is to be calculated as 1 upon NFB into bracket 4M upon DB minus W. So this is the general overview related to the designing. Now let us come to the numerical associated with this. A tall vertical vessel of 1.5 meter in diameter and 13 meter in height. Let us assume that this vessel is having a diameter of 1.5 meter and total height of 13 meters. Is to be provided with a skirt support. The weight of the vessel and its content is 80,000 kg. So weight of the vessel, that is 80,000 kg, that data is provided. Then the diameter of the skirt is equal to the diameter of the vessel. Both the diameters they are matching, that is 1.5 meters is the diameter. Then the height of the skirt, that is the bottom height of the skirt, is 2.2 meters. So what will be the total height in that case? It is the 13 meters, that is the height of the column, plus 2.2 meters which is at the bottom. That is nothing but 15.2 meters, that will be the total height that is to be taken for calculation purpose. Then the height of the skirt, okay, the wind pressure acting over the vessel is 100 kg per meter square. That is, as we have assumed that this vessel is below 20 meters high, so we are taking the P1, that is the load. So wind pressure that is acting over the vessel is 100 kgs per meter square. And where the factor K1, which is the depending on the shape, that is the 0.7 for cylindrical vessel. C is the seismic coefficient, which is having the higher value of 0.08. Then the permissible tensile stresses of the skirt material, which is equal to 960 kgs per meter square, and the permissible compressive stresses is 1/3 of the yield stresses of the material. So what are the yield stresses? Which is 2400 kgs per centimeter square. So what will be the permissible compressive stresses? That is 2400 divided by the 3. So the permissible compressive stresses, that is nothing but 2400 divided by 3, because it is 1/3 of the yield stresses. And there are permissible tensile stresses also mentioned. The permissible tensile stresses that is mentioned and permissible compressive stresses that is mentioned. Means this is nothing but 800 kgs per centimeter square, and tensile stresses are 960 kgs per centimeter square. Then estimate the thickness for the skirt support. So what will be the thickness of the skirt support? That is the thickness, the total weight which is acting over this vessel, that is to be taken into account for that purpose. So the stresses induced because of the dead weight. So first we have to consider the stresses because of the dead weight, stresses because of the wind or seismic load, and from there we are going to calculate the thickness for the skirt. So this is the dead weight, the stresses because of the dead weight, that is the total weight, summation of the weight, which is mentioned in this numerical is 80,000 kgs. So that is the summation of weight, including the weight of the material plus the vessel weight, upon the pi dsk into the tsk, that is on which area this weight is exerted. टोटल स्कर्ट का जो एरिया है उसके ऊपर exert हो रहा है ये. So this area on which it is getting exerted. So this is nothing but pi d, which is circumference into the thickness of the vessel, thickness of the skirt. So we are knowing the diameter, which is 150, which is 1.5 meter, which is nothing but 150 centimeters, because it is in the centimeter. So the thickness we have written, this is also its unit is kgs per centimeter square. So this equation is written in terms of the tsk, thickness of the skirt. So FDB, which is equal to 1.69.74 upon tsk. Now the stresses induced due to the wind load, they are also to be calculated. So P, which is the one wind force, that will be equal to K1, K2, P1, P2, and the H1 and DO, where K1 is the shape factor, K2 is the period of vibration, then P1 is the wind force, wind load, H1 is the height, and DO is the diameter of the vessel. So K1 is 0.7, K2 is the 1.0. So P wind force, that is 0.7 into 1 into 100, which is the P1 that is mentioned up to the height of the 20 meters, that is 200 kgs per meter square. Its unit is kgs per meter square. And that is why we are writing here 15.2 kgs per meter square. 15.2 is nothing but 13 plus 2.2. That is 2.2 is the height of the skirt. And 13 meters is the total height of the vessel. So this is the 2.2 meter and this is 13 meters. So from the height, total height from the ground, that will be nothing but the 15.2 meters. So bending moment induced due to the wind load, which is equal to M into the P, and which is equal to P into H by 2. The load exerted at a half a distance. So this 1596 divided by 15.2, that is the total height divided by 2. That comes in 121,296 kg meter. So the stresses induced because of this bending moment, that is the M. This is in kg meter. This is to make it in the centimeters. Upon pi by 4 d O square into the TSK. We are knowing diameter of the vessel, outer diameter of the vessel. So which is in terms of the TSK. This is another equation in terms of the TSK. So bending moment because of the seismic load, that is also to be calculated then. Sorry. So bending moment due to the seismic load, that is MSB, which is equal to 2/3 CW into H, which is equal to 2/3 into the C, that is the seismic coefficient. W is nothing but the total weight of the vessel into the H height of the vessel. So that comes as the 64,853. Then the stresses because of the seismic load, this is the MSB upon pi by 4 dO square into TSK. This is to convert kg meter into the kg centimeter. This is the kg meter and kg centimeter. Because this is 150, we have written it in terms of a centimeter square. Now, what will be the maximum tensile stresses of this cord design that will be based on the maximum tensile stresses? Mention maximum tensile stresses, that is the FT, which is 960. Now, out of this FWB, that is stresses because of the wind acting at the bottom, or stresses because of the seismic load acting at the bottom. So this is 367, and the upper is 68.67. So out of this, the higher will be the 367, that is because of the seismic load. So we have taken into account the stresses because of the seismic load minus the stresses because of the dead weight, which is 169.74 upon TSK. So from here we will be able to calculate the stresses thickness required for this skirt, which comes as the 2.06 millimeters. And in case of your compressive stresses, the stresses that will be in the skirt, maximum compressive stresses in the skirt, that is the FC compressive, which will be the summation of the stresses because of the wind load or seismic load plus the stresses because of the dead weight. So this is the compressive stresses is 1/3 of the yield stresses, and the yield stresses that is mentioned is 2,400 kgs per centimeter square. So this is the compressive stresses, and the stresses because of the dead weight, stresses because of the seismic load, stresses because of the dead weight. So this thickness calculated as 6.7. Now out of these two, the 6.7 is the higher thickness. So in general case, the compressive stresses that will be more. So we are using the compressive stresses to calculate the final use of the thickness. So 8 millimeter thickness for the skirt support, that will be suitable. So this is the calculation for the thickness of the skirt support. Now the next numerical that we will see, this is the tall vertical vessel. Now in this numerical, we are simply calculating the stresses. Stresses because of the seismic load, stresses because of the wind load, So a tall vertical vessel 2.2 meter in outside diameter and 34 meter in height. These are the simple calculations. However, this is done for 34-meter height. That means the height difference of 120, 100, which is taken as the wind force, is taken as 100 up to the height of 20 meters, and above 20 meters, the wind force that is taken as 200 kgs per centimeter square. But some changes has been mentioned in this numerical. That is, the wind force over the vessel is 128 kgs per centimeter square. That is the average wind force that is mentioned for this height of 34 meters. So, instead of taking the individual, that is for up to the height of H1 and then above the H2, we will be considering the total height of 34 meters with the wind force of 128 kgs per meter square. So the height has a shell thickness of 14 millimeter. This is the outside diameter that is mentioned as 2.2 meters, and the thickness of the insulation, shell thickness that is mentioned as 14 millimeter. Then the corrosion around that is not necessary. The vessel is insulated with a 80 millimeter thickness. So they what to do with this 80 millimeter thickness? When the outside diameter that is mentioned, then the use of this shell thickness is of no use because we are considering the outside diameter only. But this thickness is also mentioned, thickness of the insulation, which is the over this vessel. So vessel outside diameter is 2.2 meter and thickness of 80 millimeter that is to be added, that will make the total area exposed diameter. So the total exposed diameter has to be taken into account. For that purpose, we will add this 80 millimeters, that is 1.6, that is to be added, 16 that is to be added here. So this 2.2 that will be increased to 2.36. 2.2 plus 1.16. So that will become 2.36. So this is 2.2 meter plus 80 millimeter into 2, that is 1.6 centimeter, 0.16 centimeter. So that will make the 2.36. Now the wind force that will be, which is equal to PLW, which is equal to K1, K2, P1, H1 into the DO, and PUW, which is equal to K1, K2, P2, H2 into the DO. So here 128 again, that is same. Here also 128, that is same. Even though instead of that, we can simply calculate 20 plus 14, that is nothing but the 34. That will give you the same result. Then at this stage, we have calculated it individually also. That is PLW into the H1 by 2 plus PUW into bracket H1 plus H2 by 2, which is going to give you 42291 into the H1 by 2, and this 2960.4, 2960.4, that is nothing but PUW into the H1 plus H1 by 2. Yeah, H2 by 2, that is 14 by 2. So this will be in terms of the kg meter, this bending moment. Then the stresses. The bending stresses induced in the axial direction, that is the MW upon pi by 4 into DO square into the TSK. So which is mentioned as 471 kgs per centimeter square. So 4 into this bending moment, that is this bending moment that is mentioned. This is unit of kg meter, so we have converted it into the kg centimeter, and this is pi by 4. This is pi by 4 into the diameter do into the 1.4 thickness. Then the bending moment due to the seismic load, which is taken as MSD, which is equal to 2/3 CW into the H, which is equal to the 2/3 into 0.08 into the total dead weight into the total height. So this is the bending moment having the unit of kg meter. So the stresses because of the bending seismic load, that comes as the 310 kgs per centimeter square. Now, one can also calculate the number of anchor bolts that is required. That formula also we have seen. So a tall column of 3 meter in diameter and 30 meter in height is subjected to a bending moment of 3,03,764 kg meter at the base. The weight to use with this moment of anchor bolt sizing is 67,950 kg total weight. Estimate the number of anchor bolts required. Here some data related to the bolt that is already mentioned. Bolt circle diameter. This is 3.2 meters. Because the diameter of the vessel is 3 meter, and this bolt circle diameter that is mentioned as 3.2 meters. So this is the vessel, and to this bottom, it is the straight vertical. So this base plate will be there, and the anchor bolts, it is having the diameter of 3.2 meters. Here the bolts that will be fitted. Its diameter, that is outside diameter, that is mentioned as 3 meter diameter, and this bolt circle diameter, that is around 3.2 meters. So bolt circle diameter is 3.2 meter, and the permissible stresses for the bolt material, that is 1220 kgs per centimeter square. Anchor bolts of 50 millimeter diameter, that is are used. So 50 millimeter diameter anchor bolts, that is the 5 centimeter anchor bolts that used. So the AB anchor bolt area, which is equal to the 1 upon NFB, 4m upon dB minus W. That formula has to be used. So it is the pi by 4 dB square, which is equal to the 1 upon n number of anchor bolts into the stresses because of the permissible stresses of the bolt material, that is to be taken as FB in this numerical. The bending moment that is mentioned in this numerical also, and because of the dead weight, that is also mentioned. And this dB is the bolt circle diameter, which is taken as 3.2 meters. Then the number of anchor bolts, that will come as the 13. So in general case, one has to use the anchor bolts in multiples of the 4. So it will be the 16 number of anchor bolts that will be used, and with a bolt diameter of 50 millimeter will be the suitable to sustain this bending moment and this wind load.